When you're determining probabilities, you have to find the number of desired outcomes divided by the number of total outcomes. But sometimes we're in situations where we might have to figure out how many different possible outcomes we can have. So we'll start with a problem. You flip the coin and roll the number cube that are shown. What is the probability that you flip a head and roll a 3? So we're looking for the probability of the event that you flip a head and roll a 3. We can draw the sample space for this experiment. I could flip a head, toss a 1, flip a head, toss a 2, flip a head, toss a 3, flip a head, toss a 4, flip a head, toss a 5, and flip head, toss a 6. Or I could flip a tail, toss a 1, flip a tail, toss a 2, flip tail, toss 3, flip tail, toss 4, flip a tail, toss 5, flip a tail, and toss 6. So I have the set of all the possible outcomes. So we know that the probability is the number of desired outcomes, what you're looking for, divided by the number of possible outcomes. In this sample space, we have 12 different outcomes, and only one of these outcomes is what we desire. So the probability would be 1/12. Now this is an experiment where it's not hard to draw the sample space. But if it's pretty large, then we might have to count the number of possible outcomes using what's known as the fundamental counting principle. And what that says is that if you have an event, your first event that's going to happen, in the last case, it was the flipping of the coin. Okay, so this is our event, M. I'm just going to put a little space. I'm not drawing a fraction. Okay, so there's M different ways that M can happen. And then I have another event, N, and it can happen in different ways. So if I want to find the number of ways I can have M followed by N, then I just have to multiply the number of ways M can happen times the number of ways N can happen. In the last one, our first event was tossing a coin. And the second one was rolling the cube. Now the possible outcomes for tossing a coin are head or tails. We're not going to consider it landing on its side. So there are two possible outcomes for tossing a coin. We had a number cube that has 6 different numbers on it. So how many possible outcomes do I have of tossing a coin followed by rolling a cube? 2 times 6, which is 12. So I could have found that without looking at the sample space and then looked at how many of those outcomes fit the conditions I want. Here's another example. you're going to take a quiz and you're going to randomly guess all the answers for 3 multiple choice questions. And every question has 4 choices. What is the probability that you answer all 3 questions correctly? So first of all, we need to find the number of ways you can answer three choices, or 3 questions. Well, I have question 1, and I have question 2, and I have question 3. Now, every question has 4 choices, so I have 4 things I can pick from for question 1, 4 I could choose from for question 2, and 4 I can choose from for question 3. So that gives me a total number of 64 ways to possibly answer. Now the probability of getting them all correct just by guessing, well, there's only one way to get them all right. You have to choose the right one for the first question, you have to choose the correct one for the second, and the correct one for the third. So there's only one choice or combination of answers that's going to answer all 3 correctly out of 64, which isn't very high. So even though a multiple choice test, you might think, oh, I can be kind of familiar. Not necessarily. If you're going in there and just guessing, you're going to have, this is just 3 questions. Think of if you had 20 questions, how many possibilities you could answer, and only one of those are correct. Now, if I'm going to take objects from a single set of items, like maybe pulling names out of a hat or something like that, if the arrangement in which I pull them out of the hat matters, and I'll explain a little bit more in detail about arrangement mattering, then what I have is a permutation of those objects. So a permutation of n objects taken at a time is an ordered arrangement of all the members of the set. So if we have n things in the set and we're going to pull all of them, then the total number of possible permutations is n factorial, which we write as n with the exclamation point. And again, 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So it's n multiplied by every preceding integer all the way down to 1. So here's a set. Let's look at an example where we're drawing from the same set of objects. So we have these 4 alphabet blocks. Put them in a bag, and then you're going to draw one out and place it down. And then you're going to draw another one out, and so forth. So what is the probability that you draw the blocks in alphabetical order? So there's only one way to get the blocks in alphabetical order, right? To get A, B, C, and then D. So if I draw them out one at a time, I need to find out how many possibilities can I get of different arrangements of blocks. Well, I draw the first block, and they're all stuck in my bag of 4 blocks. So I pull one out, and it could be any one of 4 blocks. It could be A, B, C, or D. I don't know which one, but there's 4 possibilities. Now when I set that block down and go to pull out a second, I have 1 less block to choose from. There's only 3 in there now. Set that down, pull the 3rd block. I only have 2 choices now. I've already pulled out one and then the other. And then finally, all but one of the blocks has been chosen, so there's only 1 choice for the last. So the number of possible outcomes by the fundamental counting principle is 4 times 3 times 2, which is 24. So the probability that I would draw A, B, C, D is only 1 in 24 chances. Sometimes I have a whole set, but I don't want to pull everything out. I just want to pull only a certain number out. So we call this a permutation, if the order matters, of n objects taken r at a time. It's a permutation containing only r members of the set. Okay, so I'm not taking all the members of the set, all n of them. I'm only going to take a certain portion, r of them. And I have this formula for finding that. Now, this formula actually is just a shortcut for what you would find with the counting principle. Not really a shortcut actually, but just another way. Because suppose I'm going to have 7 letters, like from a Scrabble board, in a bag. And I'm going to pull them out and write down one at a time and write down what sort of quote word I might get. Maybe not actually an English word. Okay, but I'm going to pull one out, set it down, not replace it, and then pull another one out. So I have 7 letters in the bag. Right, suppose I'm only going to do that with 3 of those. Okay, now if I looked at the way I would do this with the fundamental counting principle, I would say, well, my first draw, I'm going to have 7 different choices I could choose from. There's 7 letters in the bag. Now once I take that out, then I have 6 left to draw for the second letter. Then after that, I only have 5 for the third. So by the fundamental counting principle, that turns out to be 210 different ways to make 3-letter words, assuming that they turned out to be a word and you didn't get XQT or something crazy. But look at this permutation formula. Okay, if I follow the permutation formula, so I'm going to have 7 things and I'm going to choose 3 of them. Then on the top I would have 7 factorial, and on the bottom I would have 7 minus 3 factorial. Well, that's 7 times 6 times 5 times 4 dot 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 dot, all the way down to 1. In fact, I think I'm just going to write 4 factorial. And this, we have to follow the order of operations. This factorial does not distribute. So 7 minus 3 would be 4 factorial. And all of these are multiplied together. So what happens here? Those 4 factorials cancel each other. And I just end up with 7 times 6 times 5, which is 210. So I could use either way, as long as order doesn't matter. As long as order does matter. Okay. So we have 9 players on this team. Okay. Now, first of all, I want to find the batting order for all 9 players. Okay. Is the possible number of outcomes found using permutations or combinations? We haven't talked about combinations yet, but the difference between a permutation and a combination is if rearranging changes your outcome. Okay, so suppose I chose Fred to bat first, and then Joe to bat second, and Dion to bat third, and so forth. Is that a different batting order than choosing Joe first, Dion second, perhaps Frank third, and then let's pull Frank up here last, up here, so we have 4 batters here, and then we'll choose Fred. Okay, so when you're going to give that batting order to the press box, or whether it's their starting 5 and what positions they're playing, you're going to give them that batting order. If you switch these around, that's not the same batting order. Okay, so these are different batting orders. So this is a permutation. And in this case, he's going to determine the batting order of all the 9 starting players. So this is a permutation, and we could write this 9 choose 9 if we want and put it in the formula. Or we can just say, well, since I'm using everything, then the answer is going to be in factorial. And these factorials, which in this case would be 9 factorial, get large very, very quickly. And that's one reason that you might want to use a calculator in calculating these. 9 factorial is 362,880. That's a lot of different batting orders that you can have. And that's how many you can have. Now, just to show you that this turns out to be like this, let me use the permutation formula. Permutation of 9, choose 9, would be 9 factorial over 9 minus 9 factorial. 9 factorial over 0 factorial. Now, 0 in the bottom of a fraction is undefined, but 0 factorial is defined to be 1. So I'm going to get the same thing in either place. So you want to keep that in mind. 0 factorial is defined as 1. 0 factorial, there aren't any integers less than 0. So realistically, it may not seem to make sense, but we define it that way so that our formulas will work out correctly. Now, a combination is a selection in which the order doesn't matter. So suppose I have the 9 batters for a team. Okay, and I want to look at how many ways I can send 3 of them to the locker room. So I have 9 to choose from, right? But I'm only going to pick 3. So in this case, I ask myself, well, if I chose Fred, Joe, and Dion to go to the locker room, is that a different choice than if I sent Dion, Fred, and Joe in another order? Am I still sending the same people to the same place? Yes. So what I'm talking about here is not a permutation. I'm talking about a combination. Okay. So this is what it means. The order of selecting the objects does not matter. A combination of n objects taken r at a time. We write it like this. So I'm going to have n objects I'm pulling from, the 9. And then how many am I going to take out of those 9? I'm going to choose 3. Okay. If I were to put these numbers in here, okay, so that in this case it would be n factorial over 3 factorial, that's how many I'm choosing, times 9 minus 3 factorial, which is 9 factorial over 3 factorial times 6 factorial. Now I can put this in a calculator, or I could go ahead and say, well, that's 9 times 8 times 7 times 6 factorial, instead of writing it all the way down to 1. Divided by 3 factorial over 6 factorial. Those will cancel. If I were to find the permutations, it would be 9 times 8 times 7. But again, here I'm not wanting a permutation, I'm wanting a combination. So I still left dividing by this 3 factorial. Why am I doing that? Well, 3 factorial tells me how many different arrangements I can make from 3 people. And since each arrangement is a repeat, I'm dividing out the repeats. So that's 9 times 8 times 7 over 3 times 2 times 1. I don't have to write. 3 goes into 3, 9. 8 goes into 2, 4. So there's 56 different ways, or 56 different combinations, I should say, that I could send of 3 people to the locker room. So here's a problem. A fundraising committee selects 4 of its 12 members to serve as ushers at a fundraising event. So we want to know, can we use permutations or combinations to find this number? Well, if I'm just choosing them all to be ushers, I'm not assigning one to, I want you to be an MC, I want someone else to be a hostess for a table, I want someone else to be an usher, and I want someone else to perform. Those are all different jobs. And when you assign jobs, the order you assign jobs matters. But these are not assigning everybody different jobs. I'm just going to find 4 ushers. Okay, so this would be a combination, because if I select J, and I'm going to Fred, Wilma, and Scooby, I don't know, I use names from cartoons all the time. I don't know who J is, I just put that down first, but then these are the same ushers. If I put them in a different order, I have the same set of ushers. In this case. So the order doesn't matter. Now the best thing I can think of explaining the difference between a combination and a permutation is when you deal out a 5-card hand of, say, poker or whatever, and you get those cards. Everybody looks at their cards. First thing they do is kind of put them in order, but putting them in a different order does not change the hand you have, right? So if it doesn't change the outcome, then you're going to be looking at combinations. So now let's find how many different groups of ushers are possible. So I'm going to have 12 things, and I'm going to choose 4 of them. I'm going to find the combination. So if I want to use the formula, I would say that's 12 factorial over 4 factorial times 12 minus 4 factorial. So that'd be 12 times 11 times 10 times 9 times 8 factorial over 4 factorial times 12 minus 4 is 8 factorial. Those will cancel. If I want to simplify this fraction, write 4 factorial is 4 times 3 times 2 times 1. The 3 goes into 9 3 times. The 4 goes into 12 3 times. The 2 goes into 10 5 times. So I have 3 times 11 times 5 times 3. And multiplying that out, I would have 9 times 11 would be 99 times 5, which would give me 495. That seems like a lot. And it is a lot. It doesn't take very long to grow when you're using factorials.